This is our final project on our car jack assembly using Solidworks, class DFT170 Engineering Graphics by Eli Hayes, Julius McLemore, and Aiden Tarble. Instructor Dr. Hans Chapman, Spring Semester 2025. These are our reference images. Figure 1 shows the car jack that we were given to model. Figure 2 shows our final representation of the car jack assembly with some slight tweaks. Brainstorm and design. Figure 3 shows the sketch of our side panels. Figure 4 shows the sketch of our pistons, the front, right, and top views. Figure 5 shows the sketch of our lift, and Figure 6 is the sketch of our linkage arms.
Figure 7 shows the frame of the car jack made in SolidWorks. We drew a sketch and mirrored it to make it symmetrical. For the handles, we used reference geometry. We used a reference plane and used the sweep tool to drag a circle along an arced path to make the handle. And on the right, we used the revolve tool after making a sketch to create the front cylinder that you can use for easy mobility. Figures 9 and 10 are both part of the handle. They're made pretty similarly by drawing a circle and extruding it. And then at the base of the circle, we drew another sketch and extruded that. Then we cut holes in there for basic fasteners and chamfered the edges. Figure 11 shows the piston on the inside of the mechanism. We drew a circle and extruded it. Then, for the right side, we drew a rectangle and extrude cut. And on the left side, we drew a sketch, mirrored it, and then extruded it. Afterwards, we filleted it and added holes with the extrude cut for basic fasteners. This is the lifting surface. It shows a circle that we extruded, and at the bottom, there are rectangles that we extruded and mirrored, and then we put holes for fasteners on the sides. Figures 13 and 14 were also made pretty similarly. They're both linkage arms. Figure 13 shows linked linkage arms that were connected with the extrude and fillet tools. Figure 14 shows a linkage arm that has an extruded circle on the back, and that is to join the gap between the parts and also to allow for more room between the parts. Figures 15 and 16 show different kinds of basic fasteners that we made. If we were making a real car jack, we would have used threaded fasteners, but for this we're just trying to show the basic moving animation. So we made these basic fasteners, both made with the revolve tool, and then the left one we drew a polygon and extruded that, the right one we extrude cut an X. This shows the drawing document with our orthogonal views and our isometric view. We have detail A that shows the inside piston working, section D that shows a cut through the center that shows all the mechanisms working together, and auxiliary view G that shows a view from the slant of the frame.
Here the exploded view shows each individual part and how they go together. The simulation with 5 pounds of force showed us that we needed to use alloyed steel and merge the linkage arms to support the weight of the saddle. The animation shows by pulling the handle, it pushes the piston forward, thus lifting the saddle up.
Our concluding remarks consist of, through brainstorming and communicating effectively, it led to different ideas and solutions to create our final project. Our group sketched out all of the parts for our assembly to plan out our model using pencils, rulers, arc templates, and protractors.
We worked together to model the different parts using the extrude, mirror, revolve, and reference geometry features.
Given a real-world situation, it would be much harder to create and design a standard car jack. Our simulation showed we would need stronger arms, and by making the arms bigger, it would give more support for heavy weight on the lift. Our drawing document is used for accurately showing the different orthogonal views, also including detailed section and auxiliary views.